Well, we're going to be studying some more about the mysteries of creation tonight.
Praise God. Hallelujah.
Things that are hidden in creation that most of us didn't even know until we went to school and studied some about science. Remember, the one great problem that everyone is having in this area, besides ourselves, is that of time. There are too many proofs. Some of them are pseudo-proofs. We looked at some chronometers last week that were pseudo-proofs that prove that the Earth would have to be quite a bit older than we conservative Christians would have to say. We looked at such things as we looked before at the fossils. A lot of these we'd looked at before. We looked at oil and coal deposits, mountains, light from stars, salt content in the oceans. This is just a partial listing of some of the chronometers that are used. Petrified wood, the coral reefs. We said these great coral reefs that do exist in the world would have had to have been formed sometime since the flood, because the flood would have destroyed any coral reefs that had existed prior to that. Cave formations, the stalagmite and stalactite. Remember the examples we gave you there that just don't fit into the theory of uniformitarianism. You've got a bath that got trapped in one of those. And on Lincoln Memorial, they're already 5 feet long, and that was built in this century. 45 years between the time it was built in the 20s and the time that picture was taken in 68, I believe, that I showed you last time. And there you've got some of these, what they call cave formations, that were already 5 feet in length. So those were some of the scientific chronometers that are used to help substantiate their practically universal belief that the Earth is around 5 billion years old. Now we've got one more of those to look at tonight. They'll probably sum up what we want to say about the scientific views concerning the age of the Earth. That view still is around the 5 billion mark for the Earth, around the 1 to 2 million mark for humankind. But we want to get into another geologic, really a chemico-geologic chronometer that is used, probably one of the more important ones, and that is the subject of radioactivity. A lot of people toss around the term radioactivity and really don't even know anything about radioactivity, what radioactivity is, what causes radioactivity. The fact that you come into contact with radioactivity every day of your life is surprising to a lot of people, because all they can think of, whenever they think of radioactivity, is an atom bomb, and then the radioactivity destroys you. But you can subject yourself to sometimes, a fairly high level of radioactivity and still live. Doesn't mean that you'll be normal 30 years from now, but at least you'll still live, and sometimes even then, nothing at all will happen to you. Now, obviously, whenever you are exposed to a very high level of radioactivity, there are going to be some very damaging results that come quite quickly. But people generally don't know much about radioactivity except the scientists. After all, they're the ones that discovered radioactivity back in the latter part of last century, which we'll be getting to here in a moment, in 1896. So it's a fairly recent discovery. But it is very important when you discover, or when you discuss what they call the half-life theory about radioactive elements, and there are just many, many elements that have been discovered that aren't radioactive. A lot of them are man-made, at least 11 of them that I can think of. Generally, the last 11 or 12 or 13, I can't remember what, but I believe the last 11 elements on the table of elements are all man-made elements, but all of them are radioactive. But there are a lot that come quite a bit prior to that are not man-made, that are nevertheless radioactive. So, I guess a warning needs to be given here at the beginning. It's going to be quite technical, so I'm going to go slowly and try to read some things off. That way, if I have to repeat something, I won't have to think of what I said. Sometimes I forget what I say when it's something that comes off the top of my head that you're not quoting every day. It's not like I have all the laws of radioactivity memorized like a Bible verse or something. But I do know some things about it, studying it in the past, and it's a fairly interesting thing to study. So if I need to repeat something, as long as it's not too long of a thing, I'll try to go back and repeat it. But if you've read any in your book, you'll remember there's a long section there that deals with the subject of radioactivity, because it is the number one proof for the great age of the Earth. Radioactivity as well as radiocarbon dating, they're two different things. One gives our great age of billions of years, and the latter of those, radiocarbon, is not reliable back, according to them, any earlier than 50,000 years ago. But we'll be looking at both of those. So to begin with, the definition of radioactivity that I've put together from different sources to get a complete definition of what radioactivity is. Now, what would be your definition of radioactivity? So I brought one along, just handy so we can all be speaking about the same subject. Definition: it is the spontaneous emission of particles or waves of energy called radiation. The particles or the waves of energy are called radiation, and the whole subject is radioactivity. So it's a spontaneous emission of these particles or waves of energy called radiation, and subatomic particles. What's a subatomic particle? You know what an atom is, so you got to get down smaller than an atom for a subatomic particle. Well, what makes up an atom? Protons, neutrons, and electrons. So those are subatomic particles. Due to the change in the nuclei of elemental atoms. Now, it's by this definition, as well as some things that we have to attach to this, that scientists attempt to reach back to. Well, generally, radioactive dating doesn't go back any earlier than 3 billion years, but it's still a lot longer than what the Scriptures allow. And even radiocarbon dating, carbon-14 dating, takes us back, according to them, 50,000 years or 40,000 years, somewhere in that general area, which also would not be allowed by the Scriptures. But we'll say more about radiocarbon dating or carbon-14 dating when we finish looking at radioactivity. So let's break it down and look at it. The spontaneous emission. Now, that doesn't mean an uncaused emission. Everything that's in the world has a source that is something that causes it to happen. So I don't mean spontaneous in the sense that it's not caused, because the end of the definition tells you what caused it. But it means it's something that takes place very, very quickly. Of particles or waves of energy, generally known as photons, which are spoken here as radiation, and subatomic particles due to the change in the nuclei. Now that's a plural for the nucleus, which would be singular, of an elemental atom. That is, an atom that belongs to a particular element. Now, it does not have to take place in more than one. It ends up taking place in more than one. It starts in one, and then if it's not controlled, like you can control it in a nuclear reactor, if it's uncontrolled, like a nuclear bomb, an atom bomb, it's uncontrolled, and you have what they call a chain reaction of the fission of one atom, the nucleus of one atom after another. We'll discuss an atom bomb in a few moments, but in an atom bomb you have a chain reaction, a chain of events from one nucleus in an atom to the nucleus of an atom that's nearby, and nearby, and that's what produces this tremendous amount not only of energy, but of radioactive particles. Now we have to break down the definition, discuss for a moment what an atom is. This is all simple stuff, but most people really don't know what they're talking about when they use words like this. You've seen on a piece of paper a diagram of an atom, little thing that has points on it that has little dotted lines circling it from all different angles, and that's supposed to represent the electrons that are going around the nucleus. Only thing with that is the distance between the nucleus and the electrons is so tremendous that should you put a dot on a piece of paper that represents a nucleus, you couldn't draw those little lines around it for many, many feet away. So to get all that down in one little diagram about that big, that's impossible. So that's getting across something that's simply not true to you. When you see the typical diagram of what an atom looks like, if you put that tiny, tiny dot, which represents the nucleus, then you're going to have to move many, many feet away. And, of course, you can't show that all on a piece of paper unless you've got one of these giant fold-out maps, many feet, 20 or 30 feet away, to show what it would look like to see the electrons going around, spinning around that nucleus that is in the center. So an atom is composed of those things that I just said. An atom has a nucleus, which has one or more positive charges, the positive charges being caused by the presence of protons. So in other words, you can't have an atom until you have a nucleus, and you can't have a nucleus until you have at least one proton. So in other words, you can't have an atom without one proton at least being there, thereby giving us at least one positive charge. There's only one that has only one positive charge. The vast majority of them have more than one charge, all the way up to in the 90s and so forth. They can have great positive charges, which represents the number of protons available. This nucleus then is surrounded by a core, or what sometimes is referred to as a shell, of negatively charged electrons. The modern diagram and understanding of the atom is credited to a Danish physicist by the name of Niels Bohr, B-O-H-R, who made the rather substantial discovery in 1913, a Danish physicist. Now again, that's almost within our lifetime. So that's where science is with respect to all of the ages that have been before us, and them just getting around to discovering what everything is made of. We thought, things were made of this and then of that, and then we thought, oh, cells. Bodies are made of cells, but then what's a cell made of? And it's taken quite some time for scientists to get down to these small, small things called atoms, and then even smaller than the atoms, the subatomic particles, the three charges, the positive, neutral, and negative charge that make up an atom. And it's rather interesting that before we put a lot of trust in what the scientists have to say, remember all this is new to them. It's as new to us as it is to them. It's not like they've been working on this for 5 millennia and they're pretty sure about an atom and all of its properties and what goes in an atom and what you can bring out of an atom. I mean, they've done some remarkable things since 1913 and Niels Bohr, but that still was only a few years ago in comparison to how long people have been trying to guess and figure out what everything is made of. And you see, whenever you reduce everything to its smallest component, all you have is Colossians 1:17, and that's energy, where we're told that he upholds all things, which right away tells you that if he wasn't upholding it, everything would just simply break down, and that's exactly what an atom is all about. You think, how can this pulpit break down? It's composed of nothing but speeding electrons going at the speed of light. It's just that in a solid material, the atoms are much more dense than they are in a liquid material, and they're more dense in a liquid material than they are in a gaseous state. And you've got generally those three states, a gas, a liquid, and a solid. And you've got atoms in all of them. You've got protons, neutrons, and electrons, and you've got electrons that are going around the nucleus of the atom at the speed of light, if not greater. How are you going to measure, by the way, the speed of light? You're going to put a speedometer on an electron and clock it as it goes around the nucleus? Remember, a lot of these things are still in the guessing stage. These are just guesses of educated men. I realize they've got all types of fancy equipment to figure all this out, but how are you really going to find out unless you jog along beside it? and gauge the speed on how fast you go, or your pet dog or horse can go. They can probably run faster than the average man, or a car, or a jet airplane, how fast you want to get. You got to get up to something that you can put your hands on that's tangible before you can figure out how fast the speed of light really is. I mean, all these things are very interesting that, just like back in our studies about Cro-Magnon, we're made to accept these things as though they're established facts. But say, now prove to me that the speed of light is really 186,000 miles a second. How are you going to prove that to me? How are you going to prove to me that an electron really goes at the speed of light, if not greater? It's one thing to turn a flashlight on and try to run as fast as the light goes from the flashlight to the recipient of the light. That wouldn't be as difficult as trying to run around a nucleus of an atom with an electron in your pocket. That'd be a lot more difficult. You could at least attempt to be Flash Gordon and run as fast as the light goes from the flashlight to the recipient of the light. But what about when you bring it all the way down to an atom? I mean, if I'm going to work in some job outside of the job I have, I wouldn't pick science, because all of it's speculation. You never really know about things, and your theory, dear friends, is destroyed the next year. Man, Daniel 12 says, is going to just increase in knowledge and increase in knowledge, and he's just been increasing in knowledge. But every year another theory comes along that breaks down some theory that was earlier. Or if it doesn't break it down, it at least adds so much to it that it changes the whole nature of the theory that came before. I mean, you're not going to do away with the theory of electricity, but look what we understand about electricity now as compared to old Ben Franklin's days back then. Now you can, with these giant telephone corporations here in this country, you can speed little voices along with a laser beam. Now, how are you going to put someone's voice in a laser beam and send it along at the speed of light? And they can do that now. Transmit the voice, not electrically over a wire. That's old-fashioned now. You can transfer it from one place to another by a laser beam, and it'll go at the speed of light. Very ingenious man is. But he's forgotten his creator, though. That's Ecclesiastes 12:1. He's forgotten his creator. Doesn't seem to like to have anyone remind him of his creator. He wants to think he created himself. And that's what education and wisdom does for about 99% of people who ever get any education or wisdom. They make themselves their own creator. And they forget Psalm 100, that it's the Lord that hath made us. We are his people and the sheep of his pasture. But educated man doesn't like this. It's rare, 1 Corinthians 1, to find an educated scientist that will believe anything about the Word of God. And they're so rare that when you put them alongside those that don't believe the Word of God, there's no proportion there. They're practically zero, because there are very few that are willing to bow and say, now there's some force outside of what I can analyze in the test tube in my laboratory. You see, you can't do that to God. He won't let you do that to him. You can do that with all of his creation here, and that excites man. But what about the first cause? Remember, that's what we said last week. What about the first cause? Every effect has to have a cause, except God. He is as the old theologians used to say, he is the uncaused cause. And he's the only uncaused cause. That was what the early Latin theologians said about God in trying to find out, now, how long has God been around? Well, he's the uncaused cause. That means that he's been around forever. He never had a cause. He causes everything else, either directly or indirectly, but he's the uncaused cause. The Son eternally begotten, the Father and the Holy Spirit eternally present. So anyway, to get back to the atom, it has a nucleus with one or more positive charges. That depends upon the presence or absence of protons. Neutrons don't figure in right now. Surrounded by a shell of negatively charged electrons, which in essence gives every single atom a neutral charge. Atoms don't have positive or negative charges. Every atom has a neutral charge. We'll say more about that when we get down to discussing what the atomic number of the elements on the periodic table of elements mean. But every atom has not a positive or a negative charge, but it has a neutral charge. Now to give you a little history about radioactivity. It was discovered by a French physicist in 1896, just a few months after the German discovery of X-rays, both of which tie in hand. So, neither one of the discoveries made here in this country. And the first element that was discovered as being one that had the properties of radioactivity was that rare element known as uranium. And still rare. A-bombs are made, or at least used to be made, out of uranium. It's a very rare element. So it was discovered in 1896. Other events and steps followed shortly thereafter, and I'll give you just a few of those. They could be multiplied by the dozens ever since the beginning of this century up until, let's say 1970. We had some recent discoveries in 1970, so for at least 70 years you had one discovery after another in this whole field of radioactivity. First of all, in 1898, the French scientist, female, Marie Curie, C-U-R-I-E, discovered the radioactive elements known as polonium and radium, and of course found both of these in the ores that were produced by uranium. Uranium was the first radioactive element that was discovered, and in uranium ores, you see some of these are alkali alloys, and in uranium ores the elements polonium, P-O-L-O-N-I-U-M, and radium, R-A-D-I-U-M, were discovered by Marie Curie in uranium ores. 2 years later, a relative of hers, Pierre Curie, you can tell what country they're from, classified the first two known types of radiation: alpha decay and beta decay, or alpha rays and beta rays, taken, of course, from the Greek alphabet. Alpha, beta, the first two letters in the Greek alphabet. Alpha rays, or alpha decay, and beta rays, or beta decay, were the first two known types of radiation. You see, you can have a radioactive element like uranium and not understand what type of radiation is there. We gave you a definition of radioactivity before, but there are different types of radiation. In other words, radiation can be caused by different types of things. One of these, an alpha ray, another a beta ray. Then the same year, 1900, a man by the name of Paul Ulrich Willard, V-I-L-L-A-R-D, Paul Ulrich Willard discovered the third type of radiation known as gamma rays. In 1902, Ernest Rutherford was the first to recognize that nuclear changes accompany radioactive emissions. In other words, now they have traced radioactive emissions or radioactive phenomenon back to something that has to do with something that's nuclear. Nuclear simply refers to the nucleus of an atom, because at this beginning stage here, they didn't have a definition of what radioactivity was. They were trying to get all the discoveries put together and find out now just what is radioactivity and just what causes radioactivity. And by this time, with Ernest Rutherford, 1902, they have traced radiation, radioactivity, and its peculiarities back to nuclear changes. In other words, something was taking place in the nucleus. Now, if you go back up to the definition, you can see this is part of the accepted definition today, that the end part there, that it's due to the change in the nuclei of elemental atoms. You know, it's one thing to know something about radioactivity, it's another thing to be able to trace it back to the nucleus, and then even more than that, to specific things that occur within the nucleus or specific things that occur outside the nucleus that affect the nucleus in some way. And most of them, of course, are due to the latter cause. In 1905, this was a rather long name, Egon Ritter von Schweidler, Schweidler. Egon Ritter von Schweidler, this is an important discovery, formulated the statistical laws for radioactive decay. Now this becomes very important because it's radioactive decay and the so-called half-life theory of the parent and daughter elements that figures in to the so-called 3 billion year old datings of various rocks in the Earth's surface. So the 1905 discovery of the formulation of the statistical laws of radioactive decay is quite important. Now for the next 40 years, from 1905 to 1945, you just have one discovery after another. You have discovery of rubidium, you have a discovery of thorium, you have the discovery of all types of different elements. Today there are around 100 elements that are known, and during this process many of these were discovered. Many of these that were radioactive were discovered during this time. Uranium in 1896 being the first of those, and shortly thereafter for at least the next 50 years, for the most part, all of the other elements that at least today are known to be radioactive were then discovered. So we get up, I'm skipping over that 40-year period because just one discovery after another with the Curies, with Rutherford, some of these names I've mentioned before, they continue to build upon theories they themselves had established before and find radioactivity being manifested even in a gaseous state. So come up to 1945, July the 16th, and we have the first atomic bomb set off in Alamogordo, New Mexico. The United States was the first country to develop a nuclear weapon, and it was the first to test a nuclear weapon, July the 16th, 1945. During some of our lifetimes here, the first A-bomb set off in Alamogordo, New Mexico. Alamogordo. Now, if you know anything about history, you probably can guess why that was done on July the 16th, not necessarily July the 16th, but July of 1945. Remember, we're at war now with Japan. Germany, for all practical purposes, has folded, but we're still at war with Japan at this time. And so before we're going to set off bombs in Japan, they test one about 3 weeks or so before the actual dropping of the bombs on the two cities in Japan. So the first one was tested right here in this country, in New Mexico. I guess you realize that states like New Mexico and Nevada and Utah and so forth, practically the whole state is owned by the federal government. Those are not the best places to live because the vast amount of territory in those states is owned by the federal government for all of the obvious reasons. One being, you've got to remember that we came to this country and moved westward from the East Coast to the West Coast. And so the western states came along a lot later than the 13 original colonies back on the Atlantic seaboard did. And by the time these western states, like Nevada and so forth, are discovered, the old federal government has stepped in and just claims everything for itself and never let go of it. Not that there's anything wrong with that, because this is where, the major military bases are and Air Force strips and where nuclear weapons are tested. Then on August the 6th, 1945, a uranium A-bomb was dropped on Hiroshima, Japan. The second atomic bomb to be detonated in human history. August the 9th, that wasn't enough. You see, even the Japanese didn't understand a lot about A-bombs, or they would have surrendered after that first one. 3 days later, we dropped a second atomic bomb. This time it was a plutonium atomic bomb. Both uranium and plutonium being radioactive elements on the Japanese city of Nagasaki. The third atomic bomb to be detonated in human history. And of course, after the August 9th, 1945 plutonium bombing of Nagasaki, we have a quick and rather abrupt conclusion to World War II. Then in July of 1946, the next year, the fourth and the fifth atomic bombs in history are detonated in the South Pacific off the atoll known as the Bikini Atoll. We talked about atolls last week. The Bikini Atoll was a rather large atoll. Well, it's still there. But two atomic bombs in July of 1946. If I remember correctly, one was detonated in the air just to test the impact and the force that a bomb in the air over the sea would have, like this particular bomb, and another one was detonated 90 feet below sea level. In other words, in the Pacific Ocean, to see what it would cause. And you get your standard mushroom cloud, and with the one under the water, all of the great spray in the ocean that was brought up. Then from 1946 through 1958, they continued testing one bomb after another. By the way, the inhabitants of Bikini Island were removed shortly before they started their test in July of 1946. They continued testing up through 1958, and finally by 1968, plans were put into action in carrying all of the native people back to Bikini. They wanted to go back home again. And so it took around 10 years for the radioactive fallout to disintegrate enough. You see, it does decay. That's what we're going to be discussing, is the decay rate. It does decay, and besides that, it's absorbed into the atmosphere and so forth, so that the original inhabitants could go back.
For the continuation of this message, please turn the tape over.
Radioactive fallout to disintegrate enough. You see, it does decay. That's what we're going to be discussing, is the decay rate. It does decay, and besides that, it's absorbed into the atmosphere and so forth, so that the original inhabitants could go back. I think it cost the United States around $3 million for the relocation of those people, Polynesian people, that they didn't belong to us and we didn't belong to them. We didn't have any right blowing up their island like that and making them live for 20 years somewhere else. And then finally, in '68, we got around to moving them back. They never got back there to the early '70s, but the red tape of governmental machinery finally got into first gear and got going anyway on getting all of the people back. So that takes us roughly and briefly from 1896 right up to 1968. Now, we haven't been detonating that many atomic bombs because of the agreements we have with the Soviet Union, but the Soviet Union just set off an atomic bomb recently. They try to do it up north of the Arctic Circle so no one can find out about it, but there's no way you can set an A-bomb off without all types of measurements being taken by laboratories all over the world. I mean, it's going to register just like a volcano. And so that's going to pick up on a Richter scale fairly quickly, and it does. And that's how we discovered a recent attempt, or was a successful attempt, of the Soviet Union to detonate an atomic bomb. Around 10 nations, that's not precise, but just to give you an approximate number, around 10 nations today have the capability of manufacturing and detonating an atomic bomb. The United States was first, followed by the Soviet Union, followed by Great Britain, followed by China, followed by other countries since then, Argentina being the most recent one. So that's really not many nations when you think about it in comparison to all of the nations on the globe today. Around 10, or just a little below that, have the capability of detonating an atomic bomb, and that includes little old scrappy Israel as well. Israel is the smallest nation that has an atomic bomb, and they just about used it during one of their Arab conflicts back in the 60s and 70s. It was transported, I remember, underground from one tunnel to another tunnel, and they were going to use it but never set it off. Thank the Lord they did, and he fought their battles for them, and they won anyway. But little Israel may resort to using that A-bomb if she gets pushed around by any of those big neighbors. You see, we've got terrible problems going on over there. 3 years now. The Iranians and the Iraqis have been fighting one another, and now that's just escalating, and you've got tremendous warfare going on there, not counting north in Lebanon and Syria and all of the fighting going on there. So Israel still has her trump card at the bottom of the deck, and she'll pull it out whenever she needs to use it, if that's the Lord's will. Now let's move on from the history to different types of radioactivity. We've already given you three of those: alpha decay, beta decay, gamma decay. There are about 7, 8, or 9 of these. I'm not going to give you all of them, just a sampling of them. Electron capture, proton radioactivity, and so forth. One particular type that is particularly interesting because of the subject of atomic nuclear warfare is known as fission. Spontaneous fission, I believe, is a technical name for it, so you can add that onto the list of types of radiation. Alpha decay, beta decay, gamma decay, electron capture, proton radioactivity, and spontaneous or nuclear fission. And this is what has taken place and does take place in a nuclear bomb. Let me see if in a sentence I can explain to you just what takes place in a nuclear bomb. An atomic bomb, same thing: atom, nuclear, nucleus, referring back to an atom and the nucleus in an atom, so you'll understand something about an atomic bomb. In nuclear fission, you have a nucleus which is a heavy isotope. Now, an isotope is the nucleus of an atom that has more or few neutrons as compared with protons. If you've got more neutrons than protons, then you've got a heavy isotope. If you've got less neutrons than protons, then you have a light isotope. But in either case, you have an isotope. But here, in this particular spontaneous fission type of radiation, you have a nucleus which is of a heavy isotope atom. This heavy isotope is ruptured into two almost equal segments by the introduction of one free neutron. You see, in every atom, if it's a basic atom, you have the same number of protons as you do neutrons. But when you get more neutrons than you do protons in the nucleus, then you have a heavy isotope. If you have fewer neutrons and protons in the nucleus of that atom, or whatever element it might be, then you have what we call a light isotope. But this is a heavy isotope in spontaneous nuclear fission. So the introduction of a free neutron then results in the release of great quantities of energy and neutrons. And this is what produces the tremendous explosion following the detonation of a nuclear weapon or a nuclear warhead. Now, what goes on in the sun is called nuclear fusion. It's just the opposite. Here you've got a division or a fission in the nucleus. And you see, whenever you split the nucleus, it was stable at one time. Although heavy, it was still stable. And when you split that nucleus, then you are going to release tremendous amounts of energy. And not just one. You see, here, like I said earlier, is where it enters into the chain reaction. When you have one free neutron that is sent into, and this is all made up in the atom bomb, is made up very intricately and scientifically, where one free neutron is sent right into the midst of that heavy isotope and that nucleus that has more neutrons than it does protons, and whenever it bombards that and it is absorbed into the heavy isotope in the nucleus of that heavy isotope, it divides it, or it causes fission between one part of the nucleus and another part. And then whenever that happens, that releases tremendous amounts of energy as well as neutrons. So what happens? Now you've got a lot of free neutrons floating around that hit the nucleus of other atoms around it, and they split. And then they release neutrons, and these neutrons hit the nucleus of an atom around it, and so forth. You've got a chain reaction. And one after another, until finally it does wear itself out. But you get a Hiroshima or Nagasaki effect. In the sun, you have what's known as nuclear fusion, where you've got two small isotopes that are fused together. They join each other. And you still have a nuclear reaction as a result of that. And that's why every time you go outside, you're experiencing radioactivity, because the sun is a radioactive body. And it does produce gamma rays and so forth ultraviolet rays, X-rays from the sun that are quite dangerous if exposed to them too long. That's why we have our atmosphere that, for the most part, is able to protect mankind on the planet. Now, how does all this tie in with dating? That brings us now to the dating of rocks and things in the earth that ties us back into what we're saying about creation. Many of the over 100 elements that have been discovered, as I've said, are radioactive. And because they're radioactive, they thus, sooner or later, disintegrate into other and generally smaller elements. That's one property of a radioactive element. It sooner or later is going to disintegrate. And this ties in directly with what we're going to be looking at. And this rate of disintegration is fairly easy to measure as long as you can observe it. And when it gets outside of observation, such as 3 billion years ago, how do you know what decayed and how fast it decayed back then? So we have to keep that out of the picture right now. That hurts the theory. But the rate of disintegration can be measured fairly reliably as long as it can be observed. Now there are, well, a couple of radioactive elements that generally are brought up as specimens and examples of a correct method by which we can gauge the age of the earth when we measure the breakdown from the parent element, which is also called the original element, and the daughter element, which is the concluding element, and I want to give you a couple of these. First of all, we have uranium, and just for the record's sake, I'm going to be real specific and give you what you need to know about each one of these. Uranium, because it does tie in whenever you're going to do any figuring on your own, uranium has an atomic number of 92. Now the atomic number is the charge of the nucleus. Remember we said that it has to have, an atom has to have a nucleus with one or more positive charges. And so if you've got uranium with an atomic number of 92, which means the charge of the nucleus is 92, it means that you have 92 protons. Its atomic weight, it's a very, very heavy element. As a matter of fact, one of the heaviest ever discovered, much heavier than light things like gold. And you know how heavy gold is. 238.04. What is atomic weight? Atomic weight is the weight of one atom in an element based on 1/12 of the weight of the element known as carbon-12. That's just the way they weigh things. I mean, you can't put it on a scale and find out how many pounds it weighs. We're talking about atoms here. We're talking about tiny, tiny things. Atomic weight is the weight of one atom in an element based on 1/12 of the weight of carbon-12, another element. And you divide that out and you get your AW, your atomic weight. So uranium with an AN of 92 and an AW of 238.04. And thorium. You have to put both of these together in our first example, which has an AN of 90, not quite as heavy. In other words, it would be on the left on your periodic table of elements from uranium, an AN of 90, an AW of 232.038. Both of these, of course, radioactive elements, will decay into radium, helium, and lead. Not necessarily all three at the same time. Depends on the reactions that take place. Radium, helium, and lead. A second example that's used is rubidium, which has an AN of 37. Just a little more than a third of the weight of uranium. And an AW of 85.47 will decay into strontium. And then a third example, which is radioactive, is potassium. With an AN of 19, and an AW of 39.102. and it will decay into argon and calcium. Now those are the three examples, the uranium-thorium example, the rubidium and the potassium example, that are oftentimes used, the latter two more than uranium and thorium, because those two are so rare, whereas rubidium and especially potassium is found in sedimentary rock all over the place, so rubidium and potassium use more than uranium and thorium simply because of their plentifulness. Now we come to a theory that I've mentioned already tonight a couple of times. That is the half-life theory that we have to explain to show how they go about determining the age of things based on this decay rate, and it's known as the half-life theory. This theory is an attempt to use the time that it would take for 1/2 of any given quantity of an element to decay. I'll repeat that. It's an attempt to use the time it would take for 1/2 of any given quantity. It doesn't have to be the whole element, but of any given quantity. Remember, elements are made up of atoms. An atom is the smallest part of an element that still has all of the faculties of an element. When you go down to subatomic particles, you've gone below an element. So it's an attempt to use the time it would take for 1/2 of any given quantity of an element to decay. Now, theoretically, you need to get this down. Theoretically, this is then what happens. In the beginning, you have what's called the original, or generally it's called the parent element. We'll take, for example, uranium. That's a parent element. And on the basis of the half-life theory, they figure out different ages and tack them on to different things. Like when we get to carbon-14 dating in a moment, the half-life is around 5,500 years. But radiocarbon dating is not anything like radioactive dating, because radioactive dating gives you these tremendous ages. So you might have a half-life of 1.5 billion years, which means that you've got a life from the beginning to the end of that element, from the beginning of the parent to the end of the daughter element. It reaches a state called stability. Most of these radioactive elements are very, very unstable elements, and they keep reducing themselves, decaying from parent to daughter element until they reach a stable position. But for some of these, and that would give you, if you've got a 1.5 billion half-life decay rate, then you would have the Earth about 3 billion years old. Or 2.5 would give you about 5 billion years for the age of the Earth. So anyway, theoretically, you go from the parent element, which is the original, to the daughter element, which is the concluding part of the element, and the quantity of the daughter element is simply compared against the presently known rate of decay of that element, and then mathematically you can determine how long it was ago when this material existed in only apparent form. It's really simple. Let me go through it again then. You simply take the quantity of the daughter element. You see, if you've got, let's say you've got 10, and right now you've got 5. You know you've got 5 right now, and you call 5 the daughter element, and you, by your own ingenuity, found out what the rate of decay is because you watch that element now and you find out what the rate of decay is. You simply work your way back in time. It's working your way back in time and superimposing upon time your theories that happen to fit now, but that perhaps won't fit back then. And we'll find out in a moment they don't fit back then. They do fit now, but they don't fit back then. And you simply work your way back to find out how long ago was it when this element had no daughter elements in it. It was only a parent element. And since you accordingly know the rate of decay and you know how much, you know, in other words, the quantity of the daughter element present, you work your way backwards until you get to a reasonable age for the beginning of the parent element. So I'll sum it up again, the sentence I've got. The quantity of the daughter elements is simply compared against the presently known rate of decay for that particular element, from parent to daughter, as you know it now. And then mathematically, you determine how long ago it was when this material existed solely in a parent form. Since we know that potassium does decay from parent potassium down to daughter argon and calcium, then you work your way backward from argon and calcium back to potassium according to the presently known rate of decay and the quantity of the argon and calcium, the daughter element that you have now, to find out how long ago it was whenever this parent element existed in its unique state, that is, without any daughter elements along with it. Now, this half-life, they say, generally ranges, this method of decay ranges somewhere between 3 billion years to less than a second. To get from the parent to the daughter element can take anywhere, depending on which element's under scrutiny, can take anywhere from 3 billion years to, a millionth of a second. It can decay that fast. In other words, it's pretty harem-scarum out there. That's a big difference. 3 billion years and 1 billionth of a second. That one element took 3 billion years to decay from parent to daughter, and another took 1 billionth of a second to decay. How are you going to measure 1 billionth of a second? Let me give you some answers now, our answers to this whole theory. In the first place, well, I think I mentioned this before. We'll mention it again as answers to radioactive dating. Does it work? No, it doesn't work. And I can tell you why. In the first place, some of the minerals, namely the first two that I gave you, uranium and thorium, are so rare that any conclusions are simply inconclusive. Because we don't have enough of it to test to find out whether our first experiment really was true. I mean, in order to have an experiment, you've got to repeat the same thing about a half a dozen times to find out, now, is it going to be constant? Or maybe was, that weather that we had that day what really made this decay fast or made it decay slowly? So you've got to be able to repeat it. But these two elements, uranium and thorium, are so rare that any conclusions are inconclusive. Secondly, experimental errors in measurement combined with physical alterations make all of the dates very sketchy. And if you'll read an honest scientist's report, he'll say that very thing. We're not talking about things you can hold in your hand and look at. We're talking about radioactive elements and neutrons and protons and billions of years. The dates are very, very sketchy. As a matter of fact, the scientists today will generally admit that anything that was done, radioactively speaking, prior to 1950 should not be trusted at all. And radioactivity had already been known for 54 years. And what happened during that 54 years? A lot of discoveries. But scientists today are saying anything done prior to 1950 is not trustworthy. Then what are the scientists in the year 2050 going to say about us today? We always have that problem. Unless we have what we believe to be the true record, and that's here in the Word of God, because it never changes. Amen. But men's theories always change. And in the year 2050, they're going to be thinking that anything that was done during our time, sketchy, unreliable, not trustworthy, because we've got better methods now to ascertain these great ages and any decay rate that might have taken place. In the third place, a complete creation in the beginning probably included both parent and daughter elements. Just like Genesis 1 tells us, light from the stars was created already here, as though it had been going for millions of years. Then in order to have a complete creation, no doubt, daughter elements were already included, as well as parent elements, to give us the doctrine of the appearance of age, to make it appear as though things had been around, because that's the same with light, That's the same with Adam and Eve and their physical body. They appeared to have been around longer than they really were. That was true with everything. He didn't make little tiny cells. He made things full grown. So why not make the mineral and chemical resources here in the world just like everything else? Parent elements, no. That answers the whole question right there in one sentence. Because everything else was made that way. Then fourthly, scientifically it is impossible to maintain the constant rate and invariability of the decay process, and therefore the half-life theory, since earlier Earth conditions, totally unknown to us, could easily have sped up or impeded the decay rate. How do we know it's always been the same constant rate that it is today? Well, we don't know. Scientifically, we don't know. Theologically, we don't know. We don't know what the decay rate was back there prior to Genesis 6 or just after Genesis 8. We don't know what the decay rate was. Perhaps there were conditions, and we know that there were. Perhaps there were conditions that could have either sped up or impeded the decay rate process. Just because it decays so quickly today doesn't mean it decayed at the same rate back then. Just because it's so slow today, the fast ones don't matter. They don't bother anyone. Just because it decays so slowly today doesn't mean it decayed slowly back then. It may look today as though it's been decaying for 3 billion years. But maybe it did all of its decaying way back there in the early chapters of Genesis. And now it's at a fairly constant rate, but you can't prove anything by its rate today. Now, quickly, let's go to carbon-14 dating and sum this up. The carbon-14 dating is similar, but it does not yield the great ages that radioactive dating purports to yield. It generally is assumed not to be reliable any earlier than 50,000 years ago. It was developed by W.F. Libby in 1946. And it concerns the radioactive isotope of carbon known as carbon-14. Carbon-14 is a radioactive isotope of carbon. And it also has to do with cosmic rays. That means rays from outer space, cosmic rays of neutrons. Now, before carbon-14 dating and this dating process can be trusted, we have to trust several certain starting points. These must be granted. About 4 of these starting points must be trusted before we can trust this method of dating. And listen to the starting points and you'll see we can't trust any of them. In the first place, the concentration of carbon-14 in the carbon dioxide cycle must always be constant. I think the words constant is in every one of these presuppositions. In the second place, the cosmic ray influx must be constant. Now, we know from the vapor canopy that's not true. It's not been constant. We didn't have the influx back then that we have today. Thirdly, the decay rate of carbon-14 atoms must be constant. And again, that's not provable because the decay process went at a different rate prior to the flood and shortly after the flood. And fourthly, there must be a constant level of atmospheric carbon dioxide as well as carbon dioxide in the oceans. Now, different things have been subjected to carbon-14 dating, let's say the pyramids of Egypt and so forth, and you know what they prove? They prove the pyramids of Egypt to be exactly as old as the historical records prove them to be. Exactly. You dig up a bone somewhere, you find a piece of pottery somewhere, and you subject it to carbon-14 dating, and guess what? It gives you a reliable account. How long ago until back around 4 or 5,000 BC. And nothing before that's reliable at all. What does that prove? It proves what we said earlier, that it took quite some time after the flood for the stage of equilibrium to set in again. And once that stage set in, now, ever since that time, things have been constant. There have not been universal cataclysmic destructions like the Great Flood. And there was not that pre-flood world where it was covered by the water vapor canopy, and just the conditions there were entirely different than today. But once several centuries or several millennia had passed after the conclusion to the Great Deluge, then things have, since that time until now, remained fairly constant. And you try to date something 1500 BC by carbon-14 dating, it's fairly reliable. It'll give or 20 years this way or that way, or 100 years this way or that way. It's no great problem. It's not like it's a million years or something. But it's very interesting that it only goes back to 4 or 5,000 BC. It means that something before 4 or 5,000 BC happened, so that carbon-14 dating can't be taken back any earlier than that. And according to all, you see, it's not that we just got one proof. One thing after another that we say here week in and week out points to these same conclusions. Why are we ending right back up to around that same time period when equilibrium set back in, and since that time things have been fairly constant. Atmosphere and all types of weather conditions, they've been fairly constant since then. You had storms back then, you have storms today. You had a certain amount of cosmic influx back then, you have essentially the same today. Sure, the atmosphere with all the aerosols going up into it has disintegrated somewhat, but nothing compared to pre-flood, post-flood comparisons. Just a little bit from post-flood until now, there have not been that many changes in things. Therefore, things remain fairly constant. So you need to differentiate between radioactive dating, which goes back millions of years, still requiring that a variety of these things and these processes must remain constant, as opposed to carbon-14 dating that doesn't even attempt to go back millions of years, that even according to the scientists themselves can't go back any prior to 50,000 years BC, but in fact really can't go back prior to any earlier than around 4 or 5,000 BC.